Hi everyone, I'm Cecilio from Group 13, which is Data Venture to the Ducks. So let me introduce our leaders, Bong Li Zhen, and following is other members, Dan Junyan and Song He Moon. So I will have a short introduction first for our project. As we know, movies are a powerful part of global entertainment. They shape culture and generate massive revenue worldwide. With platforms like TMDB, we can now analyze the film industry using data-driven approaches. In this project, we use the top 10,000 most popular movies dataset, which includes details such as titles, genres, languages, budgets, revenues, ratings, and production companies. Our approach involved two main steps. First, data wandering to clean and organize the dataset, and second, data visualization to reveal clear patterns and trends. The overall aim is to transform real movie data into meaningful insights about industry trends, audience behavior, and the key factors that influence movie success. So let's move into dataset. Our dataset is the top 10,000 most popular movies from TMDB. Or then from Kangol, it has 1,000 rows and 14 columns with the details like budgets, revenues, runtimes, ratings, genres, and languages. We choose it because it combines both numbers and categories, allowing us to explore the industry from different angles. Our analysis focuses on 4 questions: budgets versus revenues, ratings versus box office, dominant genres and languages, and how audience engagement relates to ratings. So that's all for me. Now I'll pass the floor to my members. Thank you.
For data wrangling, first, I start by importing the essential libraries. These include the libraries like Pandas for data manipulation, NumPy for numerical operation, and visualization libraries such as Matplotlib and Seaborn. First, I load the dataset into Pandas data frame and perform an initial inspection. The next is I move to the exploring dataset. At this stage, in the dataset have 10,000 rows and 14 columns. In the df.info, you can see that there are 3 columns that contain nulls. Before moving to step 3, I decide to drop the column ID, overview, and deadline because it does not useful for further analysis. The step 3, there is no duplicate rows. The release date show that 21 rows contain nulls. To handle this, we drop the null rows because the release date contain null and is not logic. Next, we found that the vote average, vote count, budget, revenue, and runtime contain the 0 values. Budget, revenue, and runtime have 0 values is not acceptable, so I convert it to none. Then use the Seaborn plot to show that the distribution of runtime looks normal, but budget and revenue distribution looks skewed, so decide to use the median imputation to fill in the none values. Now move to step 4. The outlier detection was performed using boxplot for several numerical columns, including vote average, vote count, popularity, budget, revenue, and runtime. The result shows a considerable number of outlier in each attribute: 450 in vote average, 1,100 in vote account, 992 in popularity, 4,411 in budget, and 3,553 in revenue, and 613 in runtime. This report made it clear that while most movies cluster within a typical range, there are a significant number of extreme values. Since these extreme values represent a real-world phenomenon rather than errors, they were retained instead of being removed, ensuring that the important information about essential cases is preserved for later analysis. Now move to the last part is the additional steps. First, the further transformation include the passing to release date column. Originally stored as a string, and it was converted to a proper datetime format using pandas to datetime, open bracket and close bracket. From this, a new column, release year, was extracted as the last column, allowing for easy analysis of movie by years. Furthermore, another restructuring step focused on the genres column, which contain the list like strings with multiple genres per movie. These were cleaned by removing square brackets and splitting the value into lists. Using the .exploit function, unique genres were extracted, enabling us to analyze movie genres more effectively.
Thank you, Alan, for explaining the data wrangling process. Now I will continue by presenting the EDA part. To begin with, we firstly create a new data frame called numeric df. We choose to store only the numeric column values. This can make it easier to perform statistical calculations. For example, by using the describe functions, we can quickly obtain the mean, standard deviation, minimum, maximum, and quartile values. In addition, we can also use the median function to check the median value, or just simply refer to the 50% column from the summary statistic table here. Similarly, the sum and var functions allow us to calculate the total sum and variance for each numeric columns. Then, if we want to calculate the range, we can just subtract the maximum value with the minimum value. Moving on to uncover more interesting patterns, we use the function like group by, sort values, and head. This can help us identify the most dominant features in the film industry, like the top 10 most common genres, top 10 most common languages, top 10 most frequent producers, and also top 10 highest grossing movies. Next, we also apply a technique called binning. Here, we divide the vote average into 4 categories, which are poor, average, good, and excellent. This transformation makes continuous rating much easier to interpret, and then the result is stored inside the new column called rating categories. Now, let's shift our focus to data visualization part. To explore the distribution of neural column, we use both histogram and box plots. For histogram, we customize the bin size to make the distribution smoother. For example, the histogram of vote average show a near bell-shaped curve, but we also observe a small peak between the values of 0 and 1, which can likely indicate the outliers at here. And then, so same goes to this distribution of runtime, it also show a perfect bell-shaped curve. To make the interpretation easier, we also create a summary statistic table that support the visualizations. Then after that, we plot the box plots. The reason for using the box plot is that it can clearly show the interquartile range and make it easier to detect the outliers at a glance. And then after exploring the distribution, we then examine the relationship between columns using the scatter plot. At this stage, we raise several questions such as, do higher production budgets lead to higher revenue? Do higher rate movies earn more money? Does popularity score reflect the box office success? Does spending more money improve the rating? Do longer movies tend to receive better rating? And finally, do movie with more vote tends to have a higher rating? And then all these questions can be answered through the scattered pair we just now selectively chose. Finally, to summarize the relationship, we use a correlation heat map and matrix. For interpretation, we set the threshold as follows. Values between 0.1 and 0.3 indicate weak positive correlations. Value between 0.3 and 0.5 suggest a moderate correlation, and values above 0.5 represent a strong correlation. This gives us a structured way to judge the strength of relationship between the numeric variables inside the dataset. So that's all from me. Now I'll pass to another member to continue.
Hi madam, my name is Wong Lizhen. Now I will present the discussion for our project. Our discussion is based on 4 research questions. First, we found a strong positive relationship between budget and revenue with a correlation of 0.71. While bigger budgets often means higher revenues, some low-budget films still became big hits. Second, rating and revenue show only a weak link around 0.12. This means highly rated movies don't always translate into box office success, while some low-rated ones can still perform well. Third, we look at dominance in the industry. Drama, comedy, action, and thriller are the most common genres. English is the leading language, then Japanese and Korean films are rising. Major studios like Warner Bros., Universal, and Paramount remain dominant. Finally, audience engagement and ratings had a weak correlation of 0.25. High vote counts often means popularity, but not necessarily high ratings. Together, both measures give a fully picture of how audience respond to movie. In conclusion, our project shows how data wrangling and visualization can transform raw data sets into meaningful insights about the movie industry. We found that higher budgets generally leads to higher revenues, although there are outliers where small films became big success. Ratings on the other hand had only a weak link to box office performance, providing that critical acclaim doesn't always mean commercial success. We also saw clear dominance from genres like drama, comedy, and action, the overwhelming presence of English language films, and the power of major Hollywood studios. Audience and engagement and ratings had only a weak correlation, meaning popularity and quality don't always align. Overall, this project highlights the value of cleaning and visualizing data to uncover trends for the future. Integrating streaming and social media data could give an even more complete picture of how audiences respond to films. That's all from us. Thank you.